Now let's discuss about Blinkit or Zepto. We all know what they do. They deliver day-to-day goods, typically found in their own dark stores or convenience stores via rapid delivery. So that's what they do at a high level. And let's have a look at the requirements as usual, breaking down them into functional and non-functional. So here the first requirement is users should be able to query the availability of items by geography, something that can be delivered to them in 1 hour ETA. The second requirement is users should be able to order multiple items at the same time. So these are the two minimalistic features that we will try to focus on. The others which I just added, they are not in the scope of this discussion, which are payments or purchases. So OS is basically an indicator of out of scope, and driver routing, search and catalog APIs, and the cancellations, returns and refunds. They're good to discuss or good to have them, but I don't think they're necessary for us to discuss in this video. And coming down to the non-functional, users can connect to any dark stores or distribution center, whatever we call, within 1 hour. And the latency whenever they query for availability of items, it should be less than 100 milliseconds. And the ordering should be consistent, meaning we should not let multiple users order the same item. So need to make sure it is consistent, and we need to support more than 10k dark stores and more than 100k items in a catalog. And let's assume the traffic or the volume that we are going to receive for the system is in the order of 10 million per day. So these are the functional and non-functional requirements that we need to keep in mind while we are designing the systems. So looking at this functional non-functional, we can clearly identify the core entities, and let's go to the core entities section. So the core entities from the functional non-functional requirements, it is the item, the inventory, dark store, order and order item. So here item, you can just consider that as a simple class or representation. The physical instance of an item will be in inventory, which will be located at dark stores. So we'll try to sum up all of the inventory to determine the quantity to a specific user for a specific item. So this is the inventory thing. And here, like I said, item is basically just the representation to a user in our site or an app, kind of like, sneakers or lace or whatever the items that they want to order. The dark store, it is actual physical location where items are stored. We will use this to determine which items are available for a user. So basically this inventories that we have will be stored in this dark store. And the order is nothing but a collection of this inventory which have been ordered by user. So order item. So it's a simple self-explanatory. So these are the core entities that are identified from our above functional and non-functional requirements. Once we have clearly defined these core entities, let's not worry about each of the columns and all, like we discussed earlier. As we go deeper into our design, we will try to expand on them. The third section is the APIs, the system interface where clients try to interact. So it is basically each endpoint for each of our functional requirements. Since we are going to talk about two features, we will have two endpoints. One first endpoint is querying the availability. So this one, given a location, the latitude and longitude, along with some keyword, they can search by the items keyword, And let's also add a pagination for the results that will be displaying to the user with the page size and page number. Given this param, we return list of items. So for just a purpose of it, assuming we'll have name and quantity, so we return list of items to the user. So this is one endpoint, query availability. The other one is to place an order, so which is a simple way for an user to place an order. So here we take latitude, longitude and items that the user wants to place an order for, and the return type is going to be either order object or the failure message. Okay, so these are like simple endpoints that we can think of currently for our functional requirements. Once we have this APIs clearly defined, let's now go deeper and try to discuss one point at a time from our functional requirements. So the section is the high level design. The first thing is users can query availability of items. So here we can break down into two steps. First is we need to find the dark stores that are close enough to deliver in our in 1 hour ETA, which is our requirement. The other is, let's say somehow we found the dark stores. Once we have a list of the dark stores, we need to check inventory and return union of all of the items to the users. So those are the two steps that we need to fulfill the first functional requirement. All right, let's talk about the point one. How do we find nearby dark stores? We can build a simple internal service which maybe takes latitude and longitude and then returns list of dark stores by querying let's say dark stores table within 1 hour. Yeah, and then we can return that to the user. So this is like something we can calculate the distance using simple Euclidean distance and then return that list of dark stores to the user. This is how it will look. Nearby service trying to query our dark store table and return that based on the Euclidean distance that we calculated. Maybe I can have the structure of the dark store table as a ID column, latitude and longitude. The second step is this. Now we got the dark stores and we need to now check inventory and return union of them to users. So let's try to create an availability service which handles requests from users for availability given a specific location. So this tries to query our item table and the inventory table which will have a structure of this type: item having ID column, name column and description, inventory item ID and DSID and quantity. So this will query based on the dark store ID that we have and try to join both of the tables to get the name and description and return from this service to the users. So this is how we first find out the dark store, and using that dark store we try to join the items and inventory table by matching that dark store ID and only get the name and descriptions list. That's what we need to do, this both operations in less than 100 milliseconds. So that's the something that we need to take care. So how can we make sure the steps that we discussed just now, it's going to happen in less than 100 milliseconds? So maybe let's try to recap on the how the flow is going to look like. So we make a request to the availability service with users locations, latitude and longitude and any irrelevant filters if he has passed on. Then this one will make a request um, to nearby service. So here this is what, so this is how it's going to look like putting it all together. So user makes a request to availability service. This fires a request to our nearby service with the user's locations, latitude and longitude. The nearby service will query this dark stores table and return a list of the dark stores to availability service. Now with the dark stores available, the availability service will query our database, the primary database, with those dark store IDs and join the both item table and inventory table with our required columns, the name and description, and then we sum up the results and return them to our client. So this is how it's going to look like for our first functional requirement. Yeah, this is something the flow will look like after breaking down into two steps: finding the dark store first and then the respective inventories from those dark stores that we found. Let's talk about the second requirement. We'll talk about that latency in our deep dives. I'll come back to that. Let's at least now discuss at high level, and then we'll deep dive into the specific component that we are interested in. The second thing is user can place an order. The important thing that we need to consider for this requirement is we need to make sure it is strongly consistent. That is, we should not allow two users ordering the same item. So how are we going to make sure that this is achieved? So one thing, there are a couple of ways that we can think of. One is we can have two databases with a distributed log. So how is this going to work? Let's say we have orders and inventory tables. Maybe orders we can have something like NoSQL database, and inventory in a Postgres database, relational database, whichever works best for them. So that's one thing we'll have complete control on, because we are trying to maintain two databases. So the flow is, when an order is placed, we try to log relevant inventory records and then create an order record, decrement the inventory, and then release the log, so that we don't let others to access that resource and make sure that it is logged. So this is how the flow is going to look like. But the problem with this approach is, what if the first step, order is created, that is, we have created order record, but somehow server is crashed. If server is crashed, we cannot perform this operation, which is decrementing the inventory. So if we can't perform that, and let's assume that subsequent user places a request, the same request, and we try to create a record, and he might try to order the same one, which isn't the case, and that is the thing that we need to handle. So that's one thing that we cannot handle in this situation, and we can handle, but we need to be very cautious for that one. And other thing is, there's a high chance for deadlock. So let's say there are two orders having overlapping inventory, meaning, so user 1 is trying to buy item 1 and item 2. User 1 is trying to buy item 1, and user 2 is trying to buy item 1 or item 2. So both are trying to buy item 1 and item 2. Let's say first user 1 has a log for item 2 and user 2 has a log for item 2. Now user 1 is trying to wait to get hold of item 2, and user 2 is trying to get a hold of this item 1. Both are waiting for respective item to be unlocked, and none of them are releasing, so it will be a deadlock. They are going to wait forever. So that's something which causes a challenge for us if you try to follow this approach. The other approach is singular Postgres transaction. So it's a simple approach. uh, which it's simple. We try to put orders and inventory table in a singular Postgres database, and we can leverage ACID properties of our Postgres database with an isolation level of the serializable. So this ensures that the entire transaction is atomic. That means even if two users try to order the same item at the same time, one of them will be rejected. This is because transaction will fail to commit if the inventory is not available. So this is how it's going to look like, the order, and we try to perform all of those operations in single transaction. Yeah, and the cautious points is tightly, we are just trying to tightly couple this inventory table and orders table, so we cannot have a control to independently scale them. That's fine, because we are trying to address the deadlocks and consistency issue, which is very important for us than scaling individually. And also we cannot have our own choice of storing them. So for example, let's say inventory, we NoSQL database works best for that. For orders, Postgres might work best for that. So that choices we cannot make. So those are like a simple things that we are not much worried about, but it's good to have highlight this challenges. So putting it all together, this is how it's going to look like. The user customer tries to talk to any of our services through API gateway. So the user makes a request to our order service to place an order, let's say for items 1, 2, 3. The order service creates a singular transaction in our database, which is our Postgres leader. This transaction first checks the inventory for items 1, 2, 3, and if any items are out of stock, the transaction fails. And if all items are in stock or in inventory, the transaction records the order in orders table and updates the status for inventory items in this table 1, 2, 3 as ordered. And a new row will be finally created in this orders table. So, and transaction will be committed. So if the transaction succeeds, we return the order to the users. Okay, so this is how it's going to look like. Users tries to place order, and we try to write the transactions to respective tables in our Postgres database, and if transaction is successful, we return all the way order to the user. So this is how we make sure the consistency is taken care of by leveraging the transaction and a serializable isolation level. So that's how we are going to handle that. Now let's talk about the deep dives. One thing is the availability lookups. That is basically whenever user is trying to search for an item, we are not considering now the traffic and drive time issues. We're just calculating based on the Euclidean distance, based on the user's latitude, longitude, and whichever is something that is near and can be delivered in 1 hour, we are just returning that. So there's not much of a logic. How can we incorporate traffic and drive time is something we can discuss. So currently, like I said, we do have a simple SQL distance. That is what we input latitude and longitude to our dark stores table and just return nearby dark stores. So here we are not taking into account traffic or road conditions or other things, and also it doesn't take into consideration of the fact that we might have multiple data stores in the same city. That's one thing. So now the other approach is introducing travel time estimation service against all data stores. So how this is going to work is, since our dark stores are rarely going to change because they are buildings, or we can sync periodically, like let's say every 5 minutes or 10 minutes, from our dark store table to memory of our service. and then we can use a travel time service to find the travel times from our input location to each of our data dark stores by iterating over all of them. So this is how it's going to look like. The flow, we keep periodically syncing dark stores to memory of nearby service, and then travel time service is going to leverage that and also taking the input and try to calculate based on the logic that we'll have in travel time service. So assume that's a black box for now. And the disadvantage of this is basically we make too many queries to travel time service and unnecessary queries for all our dark stores. We don't want to do for all dark stores. So to avoid that, the third approach is this: we try to call this travel time estimation service against only nearby dark stores. So it is we can maybe just sync only the dark stores which are nearer. Maybe let's say we fix it by radius, let's say 60 kilometers or miles, which is most optimistic distance that can be covered in an hour, which is our requirements, and accordingly deliver the item to the user. So this is something we can only calculate the travel time against nearest dark stores. That's how we can address this availability lookups, trying to incorporate traffic and drive time. Okay, yep. So this might not be that elaborative, but it's just to give you an idea. So and later we can discuss on this if it's needed, or you can do your due diligence and search on the go and understand how it can be done. That's one of the deep dive. The other deep dive is the latency issue. So we need to make sure the items that the user is trying to search for, we are showcasing in a very less response time. So assume the order that we mentioned in our functional requirements or non-functional, it is something we receive 10 million orders per day. So assuming each user makes 10 queries per day, so let's try to convert this 10 million orders per day to seconds, and it is 10 queries per each user. So it sums up to 1000 queries per second. So and this is orders. So assuming out of all the users that are visiting our site or mobile application, only 5% buy, that is 5% of them make an order. So if 5% is 1000 queries, so then whole users queries is going to be divided by that 5%, it's going to give us 20k queries per second. So this is the traffic that we need to handle and make sure our system delivers the results in very less response time and less than 100 milliseconds. So how can we handle this scale of very high read heavy traffic? This can be addressed using two approaches. One is we try to introduce a cache. So we try to add a cache for our inventory. So this is how it's going to look like. Our availability service now will have a Redis attached, where it can this service can query cache for given set of inputs, and if cache is having that content, it will straight away return the results to user. If we miss that, we'll do a lookup on this underlying inventory database and then write the results into our cache. Maybe we can set our time to leave as 1 minute so that results are fresh and not stale. So this one way we can take care of that. The other, and again the challenge here is we need to make sure the Redis is always in sync with the actual data that we have in our database. So that's one thing. The other approach is leverage a concept of read replicas and partitioning. So we try to have a one master write Postgres instance, and others are all read replicas, and also we try to partition by region IDs. The thing here is, since we only read inventory from nearby dark stores, we can group them by region IDs. So let's say pin code, first 3 digits of a pin code. Then we can partition our inventory data based on this region IDs. Now this means that our queries will mostly go to one or two partitions rather than entire inventory table, which improves our performance way faster, right? So yeah, this is how we try to address read heavy systems by having additional read replicas. Along with that, partitioning by region IDs and query only certain records of inventory table, and this will make sure the query results are within the latency constraints. Though there might be little consistency to our read replicas, but that's fine if the user is if user is receiving stale data for a particular period of time. It's not of a bigger concern for a user. So that's how we can address through cache or read replicas and partitioning. So after putting it all together, the downside of this is basically we need to make a choice on size of replicas and carefully manage partitioning of data, and partitioning by region ID in this case, and accordingly have a good discussion on these points and accordingly design our system. Now putting it all together, this is how it's going to look like. The read replicas is what we are going to go with instead of the caches, along with the sharding. So this is how it's going to look like after introducing this read replicas and sharding techniques. So this is how our final design for the requirements that we stated above, it's going to look like. User talks to all of our services through API gateway. So we do have here now the availability service to serve the list of items that the user wants to see in our products catalog list, and then we have internal service to find the dark stores, and the other service which is order service where user can place an order. And here it's basically our Postgres leader where we are trying to have all of our tables, items table, inventory table, and orders table. So this is how we can address the requirements, and like this there are other points as well which we have not discussed, but you can just Google it on, learn it on the go, and try to add those solutions also into the systems. Yep. And next let's move on to a news aggregator system, something like Google News, and we'll discuss more on that now.